the next type of induction problem. So when we actually are proving an inequation, let's have a look at it. Still exact same idea, exact same approach. So we'll look at the first case. Notice the first case is for n is greater than 4. So it's not 4, first case is 5. So 2 to the power of 5 is 32, 5 squared is 25, and yes, 32 is bigger than 25. And so yes, it is true for n equals 5. So we will assume it's true, but this time we've got to match the conditions. So k is not just a positive integer, it's a positive integer that is greater than 4. So 2 to the power of k greater than k squared, but we're also going to assume k is greater than 4, remember. We're now going to prove the result's true for k plus 1. So we want to prove 2 to the power of k plus 1 is greater than k plus 1 squared. So let's start with 2 to the power of k plus 1. We want to get our assumption in. Our assumption was 2 to the power of k. So like we did yesterday with the divisibility problem, I can rewrite 2 to the power of k plus 1 as 2 times 2 to the power of k. But we just said 2 to the power of k is greater than k squared. So therefore, 2 times 2 to the power of k must be greater than 2k squared. That's where we have to be a little bit creative and think about where we're heading to. We want to get k plus 1 all squared, which is k squared plus 2k plus 1. I've got 2k squared. 2k squared is the same as k squared plus k squared. I want one of those k squared. The other k squared I don't want. Remember, I would like k squared plus 2k plus 1. So now, effectively, I want to show that k squared is bigger than 2k plus 1. But remember, there was another thing we assumed. We didn't just assume that 2 to the power of k was greater than k squared. We also assumed that k was greater than 4. So if I think of that second k squared as k times k, then I can say that's greater than 4 times k, because we've assumed k is greater than 4. Alright, remember what we're trying to get. We're trying to get k squared plus 2k plus 1. So that 4k, I'm going to rewrite as 2k plus 2k. So now if I can show 2k is greater than 1, well, I can use the idea that k is greater than 4 again. So 2k, that second 2k, must be greater than 8. Again, I'm using the idea that k is greater than 4. We don't want k squared plus 2k plus 8. I want k squared plus 2k plus 1. Fortunately, we're dealing with inequalities rather than equalities, and last time I checked, 8 is bigger than 1. So k squared plus 2k plus 8 is indeed greater than k squared plus 2k plus 1. So now if I read down, I've got 2 to the power of k plus 1 is greater than k squared plus 2k plus 1, which is what we were trying to prove, because yes, that is k plus 1 squared. So yep, it's fair enough to say 2 to the power of k plus 1 is greater than k plus 1 squared, but of course, it only works if my assumption was correct. Just a note on the setting out there. Notice how my signs have changed. Remember, you're reading from line to line. So what I'm saying up the top here is 2 to the power of 2k is greater than 2k squared, but 2k squared is equal to k squared plus k squared, which is equal to k squared plus k times k. But that line is greater than the next line. Now, as long as those inequality signs don't change direction, I can then read it down and go, oh, that's fine, because at some point I've said one of these lines was greater than the next line down, then it must be true that the left-hand side is greater than the right-hand side. If I now have a line where the inequality sign goes the other way around, I'm in all sorts of trouble, because I don't know now, is it greater than, is it less than? So we need to keep them in the same direction when we're doing this proof. The equal sign's fine, that's not going to affect the inequation, but it's the, in this case, greater than sign. It needs to be greater than all the way down. Alright, let's just finish it off there. Although this time I would start off with, since the result is true for n equals 5, then the result is true for all values of n greater than 4. Okay, so that's the idea of an induction proof using an inequality